So as I said last time, that Q is an issue, so we're going to spend time with Q, and then we'll also talk a little bit about B. And that is the key to getting these problems. So let's consider, our rectangular beam cross-section. And let's say that we have 8 evenly spaced laminations in it. And I'm going to consider these potential points of interest here, A, B, C, D, and E. And so put it this way, I have 8 inches evenly spaced, so that's 8 pieces, each one is 1 inch thick, each lamination, the width is 3 inches. So I can get my I very quickly, 1/12 BH cubed, it's a rectangle. So, and in this particular case, I wanted to say something about B. Well, B is constant, so not much of a challenge in this particular problem. B is 3 inches. So, okay. Let's look at the different Q's for each of these. Now, here we have these different points of interest. That means we're going to have different shaded areas. So I'm not going to show every shaded area, but I'm going to show a couple of them. So in other words, that shaded area is for a point of interest of point A. Why? Because point A is right there, and I shade the area above it. So let's look at the Q for A is going to be, D1A1. So in other words, I've broken this thing up into 8 different areas there. So we simply have D1A1 for the Q at point A. At point B, well, my shaded area for point B would be what? It would be this whole thing, which would be area 1 and area 2. So for B, it would be D1A1 plus D2A2. For C, there's my shaded area right there. So I have to do all 3 of them. So it would be D1A1 plus D2A2 plus D3A3. For D, then of course I have all 4 of them. I have 4 of them. You can see that. Oh, sorry. For D, I have all 4. D1A1 plus D2A2 plus D3A3 plus D4A4. And if I looked at point E, for instance, I could take the area below here, which would be 3 of those. And so I notice there's some symmetry here because, for E, I would have basically 3 areas. It's the same as C. So in other words, you can see that, for point C here, I have this area. And for E here, I have this area. So they're the same. And, so there's symmetry in this. E and C are the same. And then if I had, those would also be the same, A and down below there, and B and down below there. So I'm not going to calculate those. So what do we see, since tau is equal to VQ over IB, and let's just consider this loading situation for this beam, and we've done this before, so I'm not going to go through it. My shear diagram looks like this. And where is the shear the greatest? Well, the shear is the greatest at the edges. So that's where my, peaks are in the shear diagram. So if I'm looking for the most critical point, so then what I'm going to use is a V of 30 kips. So VQ over IB, I get V is 30 kips. I get my I is 128. The B is 3 inches. And then the only question is, what is the Q at the various points here? In other words, I have this laminated beam here, and I put a bolt down the middle of it. And I want to know, for instance, where is it going to shear off? In other words, I have a lot of different potential places where it could shear off because I have a lot of different interfaces between the laminations. But now I want to think about where will it shear off. So if since I've chosen my point of interest there, I want to know, where is my real point of interest that is critical along the beam cross section. So what it comes down to is, where's my maximum tau? Well, I've already got this portion of it. So for the point of interest, then what? I have to choose the point of interest with the greatest Q. With the greatest Q, I'm going to get my greatest tau. And what do I see? Well, that one's the greatest Q, so that gives me the greatest tau. That's at point D. And so point D is right there, right in the center. Right in the center of this. So let's take a look at it and see if we were going to plot it up. In other words, suppose I calculated my tau at A, well, I'd have that. That would be pretty small. Then B is a little bit bigger. C is a little bit bigger, and then D is my biggest. So I can plot that up. A is the smallest, C is the biggest. And so if I were going to plot this, there would be A, there would be B, there would be C, there would be D, and then we just already said it's symmetric. So I get all those different points, and what do I learn? I learn that my distribution of shear stress across the beam cross-section looks like that. In other words, I get my tau max at the center here, or the centroid if I have a more complicated beam. Now, that contrasts with my sigma. Remember, my sigma looked like this. Notice that, as we stated before, the greatest sigma occurs at the top and the bottom, the very edges, whereas the smallest occurs at the centroid. So I have big at the edges, 0 at the centroid, and this is just the opposite. I have 0 at the edges, and I have the largest at the centroid. So notice the tau is just, this plot is the opposite of that plot practically. So tau is opposite of the distribution compared to sigma. So that's what I want you to know. Tau is maximum at the neutral axis. Sigma is 0 at the neutral axis. Tau is 0 at the edges. Sigma is max at the edges. So this is an important page. Know this page. You just need to know these distributions. I believe you know this one. It's a little bit more intuitive. This one is not intuitive, but this is how we got it in our calculation. So what does this tell you? If I would give you a problem asking for the maximum shear stress, well, it's going to be at the centroid, at the neutral axis. So that's going to help you locate the point of interest. Okay. All right, let's look at another potential situation. So now again, I have my laminated beam, a little bit similar. I have my bolt through all the laminations. I have my possible points of interest, which is A, B, and C. Which one is going to be critical? And then I want to get both B and Q. So notice B is not constant here. The width is not constant. So I need both B and Q. So I want both B and I want both Q for these different points of interest. So if I have a point of interest A, well, the shaded area is shown, and again I have Q is equal to D1A1, and now what is my B? B is what? B is B1 because it's the smallest. So in other words, at point A, I've got a width of the 1, and I also have a width of the 2. Well, I choose the smallest one. So it's B of the smallest one, 1. Let's check out point C. At point C, the Q is going to be, again, the D1A1 plus D2A2 plus D3A3. The B is going to be, well, in this case, it's going to be B3 because right at that location we have just one width. So let's take a look at what this means in terms of the calculation. So in other words, Q is equal to D1A1, that's a small number. B1 is also small comparatively. So my Q for point C is big because it's got all these terms here. So that's big in a sense. But also B3 is also big. So how do I figure out where the most critical location is? Well, I have to calculate it because I'm going to have, when it comes in the ratio Q over B, I want the maximum Q over B ratio. The previous problem that we did, B was constant here. So I didn't have to worry about it. I just chose the place with the greatest Q. Now I can't do that. I have to want the biggest Q over B. And in this particular case, what do I have? Q over B is a small number over a small number. This is a big number over a big number. So big over big, small over small. I don't know which is the largest, so I actually just have to do the calculations. I have to do all the calculations for the different points. So that's just what you have to do. You just have to do the calculations. There's no way to tell in advance which is most critical. So, similar cross-section here. In this particular case, what my points of interest are just there or there, those two. And so given that, I guess, everything is 1 inch, and at I'm measuring from centroid to centroid here for the small one. My D is going to be 2 inches, and I guess I didn't give all of the dimensions here. Did I do that? No. So I guess I don't show what's missing here. In any event, this width is 3 inches. I guess I didn't label it. But that gives me an area of 3 square inches. So my D times A is 6 inches cubed. If I'm choosing this other point, then, I've shown the shaded area here. And now I have to do both a D1 and a D2. And again, I didn't show it, but this distance is 5 inches. So I have my the two, I'm not going to go through, you can do this for both areas, and you get D1A1 plus D2A2, and I end up with a Q of 11 cubic inches. But my B is 5 inches here, because I'm looking at the interface at this location, and that width is 5 inches. So I guess, like I say, I haven't labeled it. But so what does that mean? That means that my Q over B is what I'm interested in. So I have 6 over 3 for this one, so that's 2. I have 11 over 5 for this one, and that's 2.2. So which one is more critical? Well, this situation is more critical. So in other words, where this is going to shear off would be that location right there. We had to put the numbers in there to determine what it was. So the critical situation is here, and I do my analyses for shearing of that bolt through that location. Okay, so similar as we've done before, if my point of interest is there, I can take the area above. If my point of interest is down here, I can take the area below. So we've talked about that previously. How do I handle a situation that looks like this? So in other words, I have I've chosen my beam, or my beam is made up of 2 pieces here. It looks like that. And I have my bolt here through there. And so how do I calculate out my the B, or sorry, Q at this location? So I have my location there, and well, I have to take all of this area here so that I can get a D2A2 plus D3A3 for that. Or I could take the area down here, which is a D1A1 term. Either way is acceptable. So, this illustrates the first case, and this illustrates the second case. You can take a look at those, but that's basically how you handle that situation with this particular shape of beam. How do I handle a composite beam? Well, we're going to do the same trick that we did before. So if I have my steel wood, I'm going to transform it. And I get my transformed section. It looks like that. I expand the steel. There, my bolt goes through here like that. My point of interest is going to be there at the interface again. And what I've done with my transformed section is that, I've made my all wood beam. Now remember, we always have to do a little modification. Well, in other words, we're going to analyze the all wood, and but we have to keep in mind that the original looks like this. So what do? We transform it. We use this for all the calculations except for B. Okay, I don't calculate my B, because one way to look at it is sort of a fake B, because I made it wider. My real B is right here, the width of the steel. So that is the trick, one of the tricks you need to know for this. In other words, you do your transform section, and you use this for all the calculations except for B. In other words, you get your I and Q with this shape. And also, you find Y bar using this. Okay, so if I have, steel and steel, what do I do with that? Well, again, I make the steel wider, and I end up with a I-beam, basically. So I analyze the I-beam. I analyze this I-beam. I don't analyze this. I analyze the I-beam. Now, what happens if I have an I-beam that looks like this, for instance, and let's just say this is my eye, the web here, and for the sake of discussion, I've shown the web made of two pieces, so I have bolts going through each of these pieces. And as we all can envision, how do we handle this? First of all, I got two bolts up here, and I think we can all envision that's the B. Why? Because I'm expecting shearing to take place there. So let's just say that the single bolt peak resistance is 8 kips. Well, what do? I use 16 kips because I use FB equals 16 kips. Why? Because I've got two of them. So in a nutshell, when I'm analyzing this, I'm going to use FB as 16 kips. Here is my shaded area there, and so I'm not going to go through the Q, but you can all get the Q. So that using this area gives me the Q, using this width gives me the B. So that's what this discussion is about. But I'll also say the FB has got to be failure force in the bolt. It's got to be 16 kips because I have two bolts right there. Now remember we talked about how an I-beam is like a box. I could take both of these web pieces, move them out, and then I get a box looks like that. And since this is the same as this, I better get the same result. So what do I have then? I need to have, again, my FB would be 16 bolts, and this would be B over 2. So make sure that you analyze it in that way. You can reason it out as being like an I-beam here. So now what if the box, though, what if we change the box? So in other words, this box looks like that with the top and bottom flanges, basically, connected with vertical bolts. Now, what if we put in the bolts horizontally, like this? And then how do we handle that situation? Well, what do? We so again, my potential shearing surface is right there. And so I'm going to do it similar to the previous one. That's B over 2, and that's B over 2. My FB, because I'm shearing off two bolts, is going to be 2 times the single bolt. So I'm basically doing similar tricks, but there's slightly different configuration for the box. So this now looks similar to this. So I'm doing the same thing, but I only have, I don't have the piece over here. I don't have that. So how do I handle it? Well, it's got to be similar to this in a sense. So there's my B. Notice there is my B. And I only have a single bolt. So my FB would be the single bolt. I wouldn't double it. like I've done here. So all right, let's take a look then at this example. And so what I want you to do is, now that I've given you the reactions, I'm even giving you the Y bar and the I, so this won't take you very long. But here's all the information here, and each bolt can resist 9 kips. I want you to find the bolt spacing and the number of bolts. So sit down and pause the video and work this problem. Okay, I'm assuming that you've done that. You can draw the shear diagram. It's pretty straightforward here, so I'm not going to go through it. You get all the areas, and you draw the moment diagram. So we have that. We're going to recognize that there's my shaded area. And you can verify these calculations for the Y bar and I. So if you want to go through that. Now what I'm interested in is the Q. Well, the Q is pretty easy in this case because that area, we already handled it in terms of area 2. And so that means that my Q is going to be D2A2. Very straightforward. You've already computed D2. It's 0.191. And we know A2 is 0.15, so it's simply D2A2. I've got my Q. My B, so I can plot my V comes from where? The shear diagram. So what do we look at? We found that here's our, P positive and peak negative. I'm interested in the greatest absolute value, so I'm going to use the negative one. So my V is 8.18. The sign doesn't matter. The I we just calculated. It's there. The Q, we just did that as well. So it's just the D2A2. And the B is what? 0.1. Why? Because this is the smallest at the location. So there's our location of interest, our point of interest. And so at that point of interest, the smallest B is that one, which is 0.1. So I get my tau at my point of interest, and then I know that FB is equal to tau FB. So I've been given the 9 for the FB, and it's going to be equal to tau. Tau is 110.5, which we've found there. S is the variable here. And B is 0.1, so we've already shown that. Solve for S, we get 0.814 feet. The number of bolts, it's 11 feet divided by 0.814, 13 and a half, which we're going to round up to 14 bolts. So 11 feet is the original. Add all that up, that's 11 feet. So I want to know the number of bolts is going to be the 11 feet divided by the bolt spacing. So hopefully you did okay on that. All right, we're going to skip this for the time being. And we'll stop.